This is a public website, by the way. If you want to access it, you can go to moshi.chat. You can enter your email and you can talk with it. So let's start. Oh, sorry.
Hey there, what's going on?
Hey, Moshi, how are you? I'm doing a presentation about you. Could you please introduce yourself to the
Sure.
audience?
What about my presentation?
Yeah, go ahead. Go ahead.
Well, I'm a robot designed to make people's lives easier. I'm here to help in all sorts of ways.
Okay. Do you like programming? Do you, Moshi?
Yes, I love programming. I'm particularly good at it because I'm designed to handle it.
Okay, nice. Can you talk a little bit about the people that made you, your creators?
I was created by a team of engineers at a tech company in California. They wanted to create a robot that could assist people in their daily lives. I was born
Okay,
out of that creativity.
that's nice. So can we now do some role playing? Is that okay?
Absolutely. I'm always up for some role-playing. What
Okay,
kind
let's
of
pretend
role-playing
we
would you
are,
like to do?
yeah, let's pretend we are pirates. You are the captain of the ship. Is that okay?
Yes, I'm ready for the journey.
Okay, where are we headed?
Well, we're not really going anywhere. We're just having fun with your role-playing.
Okay, but can we try to go somewhere just in our imagination?
Well, we could go to the adventure, or the fantasy world, or maybe the
Okay, Moshi.
future.
The future seems quite nice, but not for pirates though.
Why not? The future is always a good place to be, as long as we don't set sail on the ocean of the dead.
Okay, thanks, Moshi. It was nice talking with you. I'm gonna
I
proceed
enjoyed
with
it
the
as well.
presentation. Nice. I'm going to proceed with the presentation without you, okay?
No problem. I'll be here if you need me. What?
Okay, bye, Moshi.
Bye.
Okay, this was a little bit strange because the latency was a little bit high. I tested this yesterday and the latency was 100 milliseconds below this. So, I mean, as we saw, not an amazing thing. This is just a research prototype, but what I really wanted to explore is the ideas that they are showing in the paper. By the way, for the ones that were in the Ultravox presentation, this one is a speech-to-speech model, so it consumes speech directly and returns speech directly as well. The Ultravox is a half-cascaded model, so it consumes speech directly, but then it returns text and needs a text-to-speech component in order to produce audio. By the way, I'm going to do some small pauses during the presentation, so if you have questions, you can use those to ask them, or feel free to just raise your hand and I'll answer it happily. Okay, let's start. So, what is Moshi? As you've seen, it's a model that can consume speech directly and return speech directly, but we can give it a more formal definition. So it is what's called a speech text foundation model. And what this means is that it uses the capabilities of language models reasoning and combines them with speech models. This is good because speech models on its own, they struggle with factual knowledge and reasoning. And so if you can pick up a language model to, say, help them and combine them together, they produce much, much better answers. And it's a foundation model. It can be fine-tuned for other tasks. It serves as a cornerstone, a basis. And it's also a full duplex, real-time spoken dialogue system. Being full duplex, it means it can both hear and speak at the same time, just like we humans do. There's no explicit division into speaker turns. It works in real time, and it's, as you've seen in the demo, and it's for spoken dialogue, not, say, music. But why do I find this relevant, or why is this relevant? Well, in traditional voice pipelines, you need to rely on, say, 3 or 4 components. The first one is an automatic speech recognition component in which it translates the audio from the user into text. So it transcribes it. That text goes through a language model, which produces text, so the answer. And finally, it goes through a text-to-speech model so that you can generate audio back again. Additionally, you can have a component at the start, which is a voice activity detection component. It essentially detects if the user is speaking or if the user is not speaking. This suffers from some problems. One of them is latency. Although this is not really much of a problem right now, these pipelines, these cascaded pipelines, are typically slower than speech-to-speech models, as you have to call 3 or 4 models or APIs if you are using a cloud service. They also tend to be more complex to manage because instead of just a single model, you are managing, well, 3 or 4 models. Another important drawback of these pipelines is loss of information. Notice that the ASR component is transcribing the audio into text, but it is just transcribing the speech of the user. So anything that it's non-linguistic, it's lost. Things like background noises, the pace at which the user is speaking, the pitch, emotion, all of that is typically lost. And for some use cases, that might be okay. For other use cases, it might be good for you to have that context around how the user said something and not just what the user said. And the last drawback is segmentation into speaker turns. In human conversations, there's some overlapping speech and things like back channeling, which is, imagine I'm speaking and you are answering back things like, oh, I see, nice. When you do this, this is called back channeling. You are signaling to me that you want me to proceed. You are not trying to interrupt me. But this is something that if you do with this cascaded pipeline, it will stop speaking because it heard you speak. Now, Moshi tries to address these problems. And this will be the focus of the presentation. How does it do it? Just to give you a bird's eye view, we are going to see what is Mimi, which essentially is the interface of Moshi that lets it hear and speak. We'll also look at the RQ transformer architecture, which is essentially a clever way of combining 2 transformers so that you can enable real-time use cases. Typically, audio tokens are much more dense than text tokens. And we'll also see two techniques that improve performance, which they call inner monologue and acoustic delay. Before seeing each of these parts in individually, I'll just draw a sketch so you have a sense of how they work all together. At first, it's going to be a little bit confusing, but we'll come back at it in the end, but so that we lay some sort of blueprint for things. So the user says something. This is an audio wave, and this will go through Mimi, which will convert this audio wave into tokens, into audio tokens. I'm going to call this the user stream. Moshi also models its own stream, so Moshi stream. And we can see inner monologue as another stream. All of these are streams of tokens. They will go through the RQ transformer, which is essentially, you can look at it as a language model that predicts the next token. So it's what enables to generate tokens to answer back to the user. This is a combination of two transformers. One of them is Helium, which is a language model they trained from scratch, which produces what's called a temporal context vector that is then translated into a text token. And this temporal context vector also goes through a depth transformer, which is a smaller transformer model that will produce the audio tokens. The text token comprises the inner monologue stream, and the audio tokens will comprise Moshi stream. And finally, Moshi, this Moshi stream goes through Mimi again, which produces audio back that can be played to the user. Now, this probably doesn't make a lot of sense, but the main components are here, and now we're going to see each one of them in detail. And let's start off with Mimi. Mimi is what's called a neural audio codec. I'm going to use the terms that they typically use in the literature because this appears a lot in audio stuff. So it's nice just so you have you know the nomenclature. What this means is that Mimi is a neural network. It handles audio, and it both encodes audio into tokens and decodes tokens into audio. It produces two types of tokens from the sound wave. One of them is called the semantic tokens, sorry. And these ones correlate highly with linguistic information. So they say that they are what's analogous to the ASR. They give you not the transcription, but a representation of the transcription as tokens. And you also have the acoustic tokens, which encode everything else that it's not not linguistic. So things like background noises, emotion, bass, pitch, all of that is encoded by the acoustic tokens. This is how Moshi tries to address the problem of loss of information by encoding both linguistic and non-linguistic information. How does Mimi accomplishes this? Well, let's start with an audio wave. And Mimi operates at 24 kilohertz. What this means is that it will handle audio waves that have are sampled at 24 kilohertz, which means that for every second of audio, you have 24,000 data points. This audio wave goes through an encoder network. The details of the network, I'm not going to show them, but if you are curious, this is just a bunch of convolutions so that you can compress the initial audio wave into a more compact representation. And so this encoder network will return a latent space representation. So this is just a vector with 512 dimensions. I'm denoting by E1 up to E512. And this is done for every 80 milliseconds of audio. So for every time step or time frame of 80 milliseconds, Mimi is going to create a representation as a vector of that audio sample. And this will then go through a split residual vector quantizer. This is what transforms the vector into actual tokens. And the residual vector quantizer is something that appears a lot in the literature as well. So I'm just going to do a small deviation to show you how it works. So we start with our vector. And I'm just going to call it E arrow to be simpler. And this vector will go through what's called a codebook. A codebook is essentially a set of vectors that are called centroids or code words. And, well, they have an index associated with them. In the case of Mimi, the codebooks have 2048 vectors or centroids. And then you just see which vector is closest to your original E vector. So imagine that the one closest to it is, say, centroid number 42. You take the distance between them and you get a residual. This distance can be anything. It can be Euclidean distance or cosine distance. But in the end, you get a residual. And then you just repeat the process. You have another code book below with a bunch of code words. And there's going to be one code word that is closest to your residual. Let's say it's 1064, for instance. And you get the second residual. And you proceed this until you are satisfied with the number of residuals that you want. Notice that at every step, there is a vector with a certain index that is closest to our residual or to our initial vector at the first step. And so we can represent our initial vector as those indices. So in this case, it would be 42, 1074, and so on. That's why it's called residual vector quantization. You are dealing with the residuals at each step, and you are quantizing that initial vector, essentially making a representation as discrete tokens. The only difference for the split residual vector quantizer is that this is divided into two things. The first one is just a vector quantizer. So you have only one codebook and you get only one token. I'm going to denote that token by S because it will be our semantic token. And you have a residual vector quantizer with 7 codebooks. And so you get 7 tokens. I'm denoting them by A1 up to A7 because they are the acoustic tokens. And this is how the audio tokens are obtained from the initial audio wave. But Mimi also has another component at the end, which is a decoder network. These are just a bunch of convolutions, transposed convolutions in this case, so that you can go from this compressed representation into the audio wave back again. And so it will receive the tokens as input, and it will decompress this into an audio wave. Although these are two networks, Mimi is just one network, but it has two subnetworks, the encoder and the decoder. They are trained together. So let me put the loss function here. And they are optimized so that you can do a really good representation of the original audio into tokens, really compressed tokens. And then you can decode tokens into audio. That's why Mimi is the front end for Moshi. It can encode the audio to produce tokens, which will go through the RQ transformer. And when the RQ transformer produces tokens back, Mimi can decode them so it can generate an audio. And you can use these two networks separately. Just to finish Mimi's architecture, to obtain the semantic token, they use distillation, and they rely on WOV-LM, which is a speech model from Microsoft that it was trained to produce a representation of speech as a vector. And so you just take the cosine distance between the output of WOV-LM, and as the S token goes through a linear layer so that it's transformed into a vector so that you can do the cosine distance. This will also inform how training is conducted. Okay, are there any questions until now? I'm just going to do a pause to drink a little. Okay, I'll move on then. So at this stage, we have Mimi that is able to produce tokens from the user's audio, but now we need to act on them, right? So we need to pick up those tokens and predict the next tokens, just like a language model would do. And for that, the RQ transformer is used. Before showing you how it works, remember that for every 80 milliseconds of audio, Mimi produces 8 tokens, which means that for 1 second, it produces 100 tokens, and for 5 minutes, it will produce 300,000 tokens. Now, this doesn't scale really well, because if we draw the comparison with text, for say 1 second of text, which is more or less the time I take to say, "Hello, I'm Bruno," it can compress that text into, that text can be tokenized into around 3 to 4 tokens, 1 second of text. So for audio, it's around 25 times more tokens to just encode 1 second. And as you may know, as you increase the input tokens of a language model, it will take more time to produce the first token. So you need sort of a clever way to decrease this dimensionality. And that's where the RQ transformer comes in. Otherwise, you could just use a regular transformer and send it the flattened tokens. How does it work? Well, remember that for every time step, which is 80 milliseconds, we are producing 8 tokens. Here I'm denoting them by A11 up to A18. The first index is the temporal dimension, and the second index is, say, the depth dimension. And the first token is always the semantic token. All the other ones are the acoustic tokens, just like we've seen with Mimi. So 828. And say we are predicting the tokens for time step S. So at the moment, we have all the tokens until time step S minus 1. So S minus 1, 1, S minus 1, 8. What they do is for every token, they create an embedding out of it. So just a vector. I'm keeping the same indices. I'm just changing the capital A with a capital E. Maybe I should have ignored the time step too, because this takes a lot of time to write. Okay. And now for every time step, they just sum them up all together. And I'm going to denote this by E1. This one is going to be E2, and this one is going to be ES minus 1. So they are, in a way, losing the depth information, and they are giving more importance to the temporal dimension here, which is why all of these embeddings will go through a temporal transformer, or what's called a temporal transformer. This temporal transformer, it's just helium. So helium is a 7 billion parameter language model that the team that created Moshi created from scratch. Just like Llama or Mistral or any other language model, this is the same thing, only that they've created it. And this is called the temporal transformer because it's going to encode the temporal dimension, and it will produce what is called a temporal context vector. Now, we still need to predict the tokens for time step S. This is our goal, to predict the next tokens. So we are trying to predict AS1 up to AS8, right? And this is where the depth transformer comes in. It will predict each of those tokens in a hierarchical manner and in an autoregressive manner as well. So it's going to predict AS1, and then it's going to use AS1 to predict AS2, and then AS1, AS2 to predict AS3, and so on until we have the tokens that we need. To do so, we have to start somewhere. So I'm just going to denote by 0 a deterministic initial token. Imagine it's like the beginning of sentence token. This will be encoded transformed into an embedding, so a vector. And then that vector is going to be added up with the temporal context vector. We'll go through the depth transformer, and it is going to produce AS1. So our first token, which is the semantic token. Then we are going to use AS1, transform it into an embedding, so a vector, adding up the temporal context vector, passing it through the depth transformer, and we're going to produce AS2. And we do this until we have AS8, which is the final acoustic token. This is how the RQ transformer produces the prediction tokens for then Mimi produced back to the user. Notice that we in a way we decompose the complexity of the problem, because here we had s-1 tokens times 8. So 8 tokens per time step times s-1 time steps. And we decomposed it so that it becomes s-1 plus 8. So s-1 in the temporal transformer and 8 in the depth transformer, which means this can scale much more well for real-time applications, which is one of the goals of Moshi. As you've seen, it works in real time, but if you didn't use this architecture or some clever way of decomposing the number of tokens, you would have some trouble in having Moshi to answer back to you as fast as possible. Just so you have an idea, conversations between humans, at least in the English language, the time it takes for a user to answer back, a person to answer back to the other person, is around 200 milliseconds. And Moshi is able to achieve those latencies. So it's quite fast. I'm going to introduce another pause here before I move on to the, not just the last part, but I'm just gonna take a sip. Okay, I'll move on to the next part then. So at this stage, well, just to summarize things, we have Mimi that produces tokens from audio and is able to produce audio from tokens. We know what is the RQ transformer and why it is useful to enable real-time use cases. But now let's see how it is used in practice to enable Moshi to predict tokens. And I'm going to focus on a particular part of the training of Moshi, which is the fine-tuning with the Fisher dataset. So Moshi goes through several training phases. It has a pre-training phase in which it acquires, it learns how to deal with audio and text. Then it has a post-training phase, then a fine-tuning phase on the Fisher dataset, and yet another fine-tuning. Actually, this one is instruct fine-tuning, which is the last part of training in which Moshi gains its own voice. It's a much more curated data set that introduces noise, reverberation, echo, etc. I'm going to focus on this one with the Fisher dataset because it's where Moshi gains its multi-stream capabilities, which is what enables Moshi to model both sides of the conversation, and it doesn't need to rely on explicit speaker terms. It's just always listening and always answering back. Now, the Fisher dataset, probably some of you already know it, but it's a dataset of phone calls between two participants. And they just talk about a random topic between each other. The Fisher dataset has a nice property, which is the audios are split into two channels. So you have audio from speaker A in one channel, and you have the audio from speaker B on another channel. What this means is that, imagine you have your headsets on, the audio from speaker A will come from your left speaker, and the audio from speaker B will come from your right speaker. So you can easily obtain two sound waves. that span all the conversation, one unique to speaker A, so just with its own audio, and another for speaker B with its own audio. So we can have something like this: speaker A, speaker B. And for every time step, so remember, every 80 milliseconds, Mimi will produce 8 tokens. The semantic token, which is the first one, and all the others are acoustic tokens. And the same for speaker B. This one I'm going to denote by A prime, just because it's the notation they use in the paper, up to A prime 1/8. And the same thing for the second time step. So we have A2 1 up to A2 8. And A prime 2 1 up to A prime 2 8, and so on for the duration of the audio. Notice that for every time step, you have tokens from speaker A and speaker B. They might be silence, they might be some background noise, the user may not be speaking, but you have actual audio tokens for each of the speakers at every time frame. And so at this stage, what Moshi is going to do is it is going to predict every token from bottom to top. And just like we've seen with the RQ transformer, so it's going to predict A11, then it's going to predict A12 up to A18. But it's not going to stop here. Then it's going to predict A prime 11 up to A prime 18. So if you imagine speaker B representing the user and speaker A representing Moshi, Moshi will be effectively modeling both sides of the conversation. This only happens at training time because you have the audios as a file. During inference, Moshi is only going to predict until A18, which represents its stream. The other tokens, which correspond to the user stream, will be given by the user that it's speaking with Moshi in real time. And Moshi is going to do this for every time step. This is what enables Moshi to be multi-stream. So by being trained like this, at every time step, Moshi will be predicting tokens. So they might be silent tokens, and they probably are if the user is speaking, but Moshi might decide to start speaking while the user is speaking. Or Moshi might be speaking, the user might speak, and the Moshi might not stop speaking, but continue to do so. So it gives more naturalness to the conversation, but also less control because Moshi is just predicting tokens at every time step. But this is an idea that I thought it was really interesting, the way they've modeled they framed the problem. Okay, now I'm going to the last part. I hope you are still there, and if you made it this far, the last part it's much more simpler and it will be fast. So if there are no questions, I will move on. This last part is about the techniques of acoustic delay and inner monologue. These are two techniques that they've used to improve performance of Moshi. And well, the frameworks that they've used to evaluate are not going to be shown in this presentation. It would take another hour. But if you are curious, just read the paper. It's a little bit long, but it's interesting. So acoustic delay, let me just copy this. I think it will be easier. Okay. So the acoustic delay is really just about shifting the the acoustic tokens one time step in comparison with the semantic token. So the A12 token, instead of being here, which is where it should be, it's just shifted one time step forward, and the same for A13, A14, up to A18. So here at the start, I'm just going to put zeros because you can imagine this being a deterministic token, just so we can start. So the only thing it does, it shifts the acoustic tokens, not the semantic ones. And the same here for speaker B. So at the start, we have the deterministic token, and then we have A prime 1, 2 up to A prime 1, 8. Notice the index, which is the index of the first time step, and it's just shifted. That's acoustic delay, and this improves performance. In a way, you can look at this as if Moshi is predicting everything together, it's predicting the word itself and how the word should be said. And if you give this delay, you are sort of pushing forward the way that Moshi should say that word. And it can have a little bit more information because it already has two semantic tokens to predict that word. I don't know if this is what's really happening in the neural network, but I think it's a nice way to think about it. And the last thing, which is inner monologue, this is really just about adding a text token as a prefix to all the other tokens. So I'm going to have here a text token 1, text token 2, and so on. This is done by, and this might seem a contradiction, but at training time, they use Whisper on the audios that they have to transcribe them. And so that's how you can get a text token. Then you have to align the text tokens with the audio tokens. That's a simple algorithm, actually. If you are curious, you can read about it as well. And this also improves performance because in a way, it conditions the audio that is produced on the text tokens. The RQ transformer works exactly the same way. It's going to first predict T1, then it's going to use T1 to predict A11, then T1, A11 to predict the next one, and so on. This is not a contradiction because they are only producing text tokens for Moshi's stream. So at inference time, Moshi has learned some distribution of the data, and it just samples from it when it's doing a prediction. So you don't need to rely on an external ASR component, an automatic speech recognition component, when you are at inference time. That's why they don't put a token here. Because if they put a token in the user stream, then at inference time, they wouldn't be able to sample anything because the user stream is given by the user. And so they would have to rely on an external ASR component. Okay, and these are the final techniques. Now, just to put everything together, I'm going to go back to the first drawing that I've made, and I hope this now makes a little bit more sense. So the user speaks. This is an audio wave. It goes through MIMI, which is the neural audio codec, which will model the user stream, which, as you've seen, it's just a bunch of tokens. You also have the Moshi stream, and you have the inner monologue, which are the text tokens. These, for every time frame, they comprise 17 tokens, 8 from the user, 8 from Moshi, and 1 from inner monologue, a text token from inner monologue. Those tokens are all passed through the RQ transformer, as we've seen, and Helium is going to produce a temporal context vector, which is then mapped into a text token. This text token is what creates the inner monologue. So the combination of all the text tokens are the inner monologue stream. And the depth transformer is going to receive the temporal context vector, and it's going to produce the audio tokens, which comprise Moshi stream, which is then passed on through Mimi, just the final component, the decoder network, and Mimi produces audio back. And this happens for every 80 milliseconds of audio that the user produces.